Welcome back, friends, to another session of fluid mechanics and rate processes. We have been looking at the balance laws, and we have already derived the integral and the differential form for the continuity equation and the momentum equation, and we have been looking at the integral form of the energy equation. So, let us continue with that. Let me just review for you what we have done. So, in the last class, we talked about the first law of thermodynamics, and we were able to write that for a certain system. So, suppose this is a system, and we can talk about the rate of change of energy dE by dt of the system is related to the heat transfer and the work done. So, Q dot is the heat transfer to the control mass system, and W dot is the work done by the system. Then we went ahead and applied this to some kind of a control volume. So, this is the inlet, this is the outlet, we also called it as the exit, and then we had made a small control volume here, and we also mentioned that there could be some work done by some control surfaces, and we wrote down this equation for the system, the control system, now for a control volume where fluid goes in and comes out. So, we use the Reynolds transport theorem, and we were able to say that suppose n corresponds to E and eta corresponds to the small e, where small e is the specific energy which is per unit mass of the system, and this consists of the internal energy and then the potential energy and of course half of V dot V. In fact, there was no density in this. Okay? And we were able to transform it using the Reynolds transport theorem, and let me give you the expression of what we did. You are actually able to write that dE dt, this is Q dot minus W dot shaft work. Then we talked about the work done by the viscous forces and the work done by the pressure forces at the control surface. Okay, so, these are at the inlet and the exit ports, and this we were able to write this as the local change of energy inside the control volume, which is now rho E dV, and of course, whatever comes out, goes out or comes in through the control surface, and that would be given as E rho V dot dE. Okay. So, we were able to apply the first law of thermodynamics from a system's point of view, a control mass, to actually a control volume, and the interpretation of these terms I explained you in the last class. This is the local accumulation of energy inside the control volume. This is the efflux. So, there is energy that leaves the control volume and then some comes in, This of course is related to the heat transfer to the control volume Q dot. This is fairly straightforward, mostly through conduction, temperature differences. And the work done, this term, the W dot term, we actually broke it down into various components. So this is the work done at the control surfaces, and we said that there could be boundaries which are kind of stationary with respect to the control volume, and there is some work which is done by some kind of a shaft, and so that is this. Then there could be some viscous work both at the boundaries and of course at stationary walls, which we said they do not contribute, and then the pressure essentially at the inlet and the exit ports, which is accounted for here. So all this was done in the last class, and then we argued that actually if you look at this term, this also has to be computed only for the inlet and the exit ports. Okay, everywhere else it is 0 because of this term V dot dA being 0 at the other parts of the control surface. So we were able to take some simplifications, and finally what came out is the following. We were able to write that the rate of change of energy inside the control volume, this could be written as Q dot minus W dot the shaft work minus the viscous work, and we were able to combine certain terms. So these are the control surface at the entry and exit only, so not the entire control surface, and we were able to combine these terms E P plus rho V dot dA. So this was the energy balance that we could write for a control volume. Okay. So the idea is now to simplify this further. Okay. So we took certain special cases. So the first special case that we take is a steady flow. Of course, when the flow is steady, then the rate of change of the energy inside the control volume, this term disappears, and then we would have simply these terms remaining over here. Okay. So I would simply write here that this implies del by del T is 0. Okay. So then we can simplify this equation. We made further assumptions. We actually went ahead and said that we will now assume that the flow at inlet and outlet ports is one dimensional. Okay. So this is a big assumption. What we are saying is that suppose there are only two ports, an inlet port and an exit port. When I want to evaluate that last term written over there, okay, which is E plus P by rho times rho velocity dot dA, then actually these terms can vary across the ports. But if I imagine that they actually do not vary across the port and the flow is one dimensional, then I can look at some kind of a value across the port, and I can get rid of the integral sign and just multiply it with the areas. If the flow is not one dimensional, then I can take some kind of an average value and then apply some correction terms and proceed with my analysis. So we are going to assume that the flow is one dimensional, but only at the inlet and outlet ports. We are not making any assumption about what happens to the flow inside. The flow inside could be very complex. I mean, there is a paddle wheel that is churning the flow, so obviously this flow is very complex. But I have chosen the control surface in an intelligent manner that I should be able to assume that the flow is one dimensional. What I could do is I could actually extend the control volume a little bit inside these surfaces, for example, and then here it is easy to see that the flow is one dimensional and close to the these areas where the volume suddenly changes. It either increases at the inlet or decreases at the outlet, then the flow may not be one dimensional. Okay, but at these locations I can assume the flow to be one dimensional. All right, if I do that, then things become a little bit easier. Then I can just express these terms as E plus P by rho at the outlet. This should be equal to E plus P by rho at the inlet and plus Q minus W dot S. And what I have done is I have kind of assumed that Q is Q dot by m dot, which is the heat input per unit mass flow rate, and similarly W dot S is actually the shaft work divided by the mass flow rate through the control volume. So this is the shaft work by the control volume. So it's by the fluid in the control volume, which is per unit mass flow rate. Okay. So I get this very simplified thing, and then I can write that E is actually simply U plus V square by 2. So because now I don't have to worry about V dot V, it's a scalar V, one dimensional, and plus Gz. So this equation therefore can be simplified as U plus P by plus V square by 2 plus P by rho plus Gz at the outlet is actually equal to U plus V square by 2 plus P by rho plus Gz at the inlet plus Q minus W dot S. In fact, I can remove the dot from this. It's understood that it is a rate, so I can make it simple. So I'm sorry I put a dot on the top of it. It is understood that this is a rate, so we can get rid of the dot and simplify the notation. All right, so we have assumed that this is for a steady flow and one dimensional at the outlet and at the inlet, and then I am able to write this energy equation in this form. So let me repeat for you that the one dimensionality is only at the inlet and the exit ports. Okay. All right. Towards the end of the last class, we made another assumption. What if the flow is incompressible? So let's look at the implication of that. So in addition to the flow being steady and one dimensional at the inlet and the outlet ports, we are going to additionally assume the flow is incompressible. Now please recall that if the flow is incompressible, then P is a mechanical quantity. It's a mechanical pressure and is not coupled with U, which is the internal energy. Recall the internal energy would depend on the temperature, for example, or maybe the density. but this P is independent of the density changes in the flow or the temperature changes. In fact, the density of each fluid element is going to be preserved simply because it is an incompressible flow. Now, if I want to take that into account and I look at this equation, then U and P are now decoupled. Okay. So, if I have a change in the temperature, it changes my internal energy, but not necessarily the pressure. So, only for an incompressible flow I will remove U and from this term and U from this term and combine them like this. So, let me now write down that equation. So, it becomes V square by 2 plus Gz plus P by rho. This at the outlet, this is given as V square over 2 plus Gz plus P by rho at the inlet. Okay. And then I have the other terms Q and Ws. So, I would say Q plus Q minus Ws, the shaft work, and I would be able to now write plus the U exit minus, so I would have a minus term here, U exit minus U inlet. Okay, so what I have done is I have taken the U terms, the internal energy terms from here and put it on the right hand side. So, here is what I say. This is some kind of a mechanical energy which consists of the potential energy, the kinetic energy, and then of course something driven by the pressure. Okay, so this term came out of the flow work, the work done by the pressure in pushing the fluid into the control volume and pushing it outside the control volume. So, this is some kind of a mechanical energy at the outlet is related to what was supplied at the inlet, and then I could have some heat transfer, I could have some work output from the control volume and certain temperature changes, okay, which are incorporated into the internal energy. So, this term I could combine, this Q term and this term I could actually combine together because they are both related to temperature. Okay, internal energy depends on temperature and the heat transfer would also depend on the temperature difference between the control volume and the surroundings, and of course how the boundary is defined. Okay. So, these terms I could combine together and say this represents some kind of a loss, a heat loss, or so these I combine as WL, which is the loss. Okay. It is essentially the loss of mechanical energy into thermal energy. So, this represents loss of mechanical to thermal energy. Okay. And therefore, I should be able to write my equation like this. So, I have V square by 2 plus Gz plus P by rho, this at the outlet, this is V square by 2 plus Gz plus P by rho at the inlet, and then the combined terms are minus Ws minus Wl. So, this is really the shaft work and these are losses. This is the energy balance equation that I have for a control volume where the flow is steady, it is incompressible, and at the inlet and exit ports I can assume that it is one dimensional. Okay, so, this looks quite simple. The energy coming in sorry, the energy coming in, the energy at the exit, and the difference of the two can be explained by the losses as well as the shaft work. Now what the civil engineers have done is, the hydraulics engineers,